voltage in arc welding. We just discussed the welding arc, and we said how the arc has three components: the cathode, the anode, and the column. And we assign voltages to the cathode, the anode, and the column. And those voltages are pretty much what dominates the voltage you would read in the panel of your welding machine. And the examples I had so far were about TIG, because TIG was easy to explain in this context. Let's bring it up one notch and see, okay, what happens with voltage in the cables? How about MIG, right? How about pulsing? Let's discuss this, because this is going to open our eyes to things that can be done or cannot be done, or technologies that could be invented, or choices we could make when we need to specify equipment. So let's talk about the most general case, that is a wire-based process. This would be MIG and metal core and flux core and subarc welding. And you'll see that extending these, we learned, to TIG is essentially trivial. So in this schematic, I have the electrode, I have the droplet, the electricity, the wire is coming in, right? The wire is coming in and melting, and the droplet will fall, and the current comes from a contact tip that is shaded here, that is copper. Electricity comes through here, goes through the electrode extension or the electrode stick out, and then the current comes out into the arc. You have already seen this, but I want to bring up some concepts that are very important. One is here where I put electrode stick out, or some people call it the electrode extension, is how much it goes out from the contact tip to the droplet. Now, where exactly this finishes is not all too clear, but the droplet in general is much smaller than the stick out. So I'm not gonna be nickel and dime over that. But so you know, one of my friends in Austria, one of the lead engineers for Fronius, he did a master's thesis just on determining how to measure properly the electrode stick out. And his conclusion is like, it depends. So we're going a little bit, being a little bit loose here, but it's not too loose, it's okay. Then from the contact tip to the workpiece, let's call it the contact tip to workpiece distance, right? And these words are important. If you look at the Lincoln Procedure Handbook, it's funny because through the whole book, they call electrode extension to what we call CTWD. The Procedure Handbook has like a little bit of a dictionary at the end, and the dictionary uses our definition too. So they are being inconsistent, and we must be consistent because these things are different. So contact tip to workpiece distance is contact tip to plate. Sounds like duh, but as you see, not everybody would agree. Electrode stick out is contact tip to droplet. And then you have the arc length. So more or less, contact tip to workpiece distance equals electrode stick out plus arc length. I didn't make it match perfectly because like the arc attachment is sometimes it's not clearly defined. So give or take a droplet diameter, this is good. But the droplet tends to be small compared to this other length. So the error is not too big. So in this case, voltage. The machine will read, when you read the voltage in the panel of your welding machine, you have to account for that. That is reading not only the voltage of the anode and column and cathode fall. These three we discussed. But in addition, you have to worry about voltage loss in the leads, right? The leads are the cable, the welding cables, right? Voltage loss at the contact tip. Here we have a sliding electrical contact. Current comes through the contact tip, and then it has to jump into the wire, but the wire is moving. So we have a resistance that is associated with that sliding contact. So we have a voltage loss there, and then we have a voltage loss in the stick out, because if I have a current going through this electrode, I'm going to have a voltage loss. That sometimes it doesn't matter, sometimes matters a lot, but it's there. So this is just reminding you that this slide that has amazing information in it, and we're going to put it to good use. So let's start. This is about what's happening in the arc, right? Column, and anode, and cathode. We'll use these numbers soon. Let's talk about resistance of the cable. So the cables have, instead of resistance, we should use the proper name, impedance. So impedance is kind of fancy for resistance, but the difference matters, because resistance is a term that relates to constant current. But if I have pulsing, then I have all kind of electromagnetic effects, right? I have inductance involved with that, right? Or reactance. And that can bring us into problems. So the effect of resistance, that is what happens in DC, plus the effect of inductance, that is an effect of pulsing, together, that is what is called impedance, right? And resistance always lowers lowers the voltage by sucking up energy. Inductance does not dissipate energy. However, inductance makes it difficult to pass higher frequency pulses. Also, inductance has the problem that can get your power lines a little bit out of sync, and you end up consuming a lot of current and causing problems in the electrical distribution at large. Okay, impedance. The symbol for impedance is Z, and Z equals resistance plus J is the imaginary number, the way the electrical engineers write it, right? Because I is current, so they call it J. And X is the reactance, right? The reactance relates to inductance in a way I'm going to tell you. We're not going to be doing complex number algebra. No, let's not worry about that. But let's use these numbers properly. So the resistance, the resistance of the leads are the electrical resistance times the length of the leads, the total length from the time the machine goes out to the time it comes back, right? Divided the cross-sectional area of the conductor. The resistance of copper, you can calculate with this formula here. That is not difficult at all. It says resistance at any temperature is resistance at 20 degrees C times 1 plus, and they have a little variation with temperature. So, and here we have the numbers that are good for copper. With this, you can calculate voltage losses on any cable. For example, if we have 400 amps, 60% duty cycle with a total length of lead of 100 feet. So you realize this is a really, really long cable and is fairly high current. This is what you would be using, for example, in civil construction, right? You have the welding machine and the guy is welding all over the floor, right? And sometimes you might be using a whole lot of current because you're welding very thick sections. So if you look at the manuals that are uploaded in E-class, and this is really good information, it says, okay, if you have 400 amps, 60% duty cycle, you should use this 2O conductor. That's just an industry way of naming the cables. But they give you the cross-sectional area, 67.4 square millimeters. So what is the resistance? What is the voltage loss? What is the power loss in the leads? Let's assume they are at 30 degrees C. For those of you who took the heat transfer class, you know exactly how to calculate the temperature of the cable. But let's not worry about that now. So the resistance is resistance at 20 degrees times this correction factor, this is the difference between 30 degrees and 20, which is actually quite small. And then times the length of the cables divided the cross-sectional area. Of course, we have to use consistent units. So we have to pass the square millimeters to square meters. And this gives us 8.2 milliohms. 8.2 milliohms is small. If you have played with Arduinos or anything like that, the resistors come in kilo ohms, right? When you buy a resistor, or mega ohms. And I'm saying milliohms. All right, sounds like little. But if I do current times resistance, the voltage loss I expect is 3.3 volts. So look at this, how important. In this example, when I look at the plate of the machine, I know that the voltage I'm reading, 3.3 of those volts have nothing to do with my weld. 3.3 of those volts are just in the cable. If the cable was half as long, I would have 1.65 volts. Right? It's and if you read the Lincoln Procedure Handbook, it says, well, don't try to anticipate the voltage loss. Just use the shortest cable you can. But in some cases, I think even if you use a short cable, it's good to be aware that the voltage loss can be significant, right? And this is what is recommended. This is what is recommended. This is not what I said, okay, let's pick something crazy. This is what is recommended. Right there, almost 3.5 volts that have nothing to do with welding. Power, if I multiply my 400 amps by these 3.3 volts, I have 1.3 kilowatts I'm dissipating in the cables. You know what? I hope it's winter because it's gonna get real warm. And if the cables that are dissipating 1.3 kilowatts are not free to cool down in the air, for example, if people put like things on top of them, insulating or cloth or whatever it is, pieces of wood, these 1.3 kilowatts have nowhere to go and the cable might melt the insulation and then burn everything around it. Can happen. Oh, yes. Thank you, Wes. If the cables are wrapped tightly, right, you don't have a whole lot of room for dissipation, right? So these type of things have happened, right? And those of you who took the heat transfer class, right, now see how it all comes together. It all comes together, right? Impedance. So let's see what the effect of pulsing is. So the reactance, right, X, the imaginary part, has this formula that is 2 pi frequency times L. L in this case is not length, is inductance. 2 pi frequency times inductance. Inductance has two components. One is due to the magnetic fields outside the cable. The cable generates magnetic fields and interacts with those magnetic fields and would generate forces which we don't care about, but generates this impedance. It generates this reactance that opposes changing of, opposes pulsing. So that's one component. And the other component is internal, that is related to skin effect. So about skin effect, you get it from this graph. I'm going to show you that this is negligible. So I'm going to put this graph. I'll do an example. But this other one is the one that matters the most, the external one, right? And same example as before. But let's say we are pulsing our weld now. We pulse it at 100 hertz, we pulse it at 1,000 hertz, and at 10,000 hertz, right? And you might wonder, like, who pulses at 10,000 hertz? And you'll see that you do. So inductance has these two components, the external and the internal. The external comes from the formula, from this formula, and gives you 52.7 microhenry, whatever those are, right? The internal, if we go to the graph, we come to the conclusion that the internal inductance is 1.52 microhenries at 600 hertz, can be 0.21 microhenries at 10,000 hertz. The bottom line, in this example, the internal impedance due to skin effect is not a big deal. Fine. So let's keep moving, having in mind that this external impedance is what really matters. So the reactance in this case, when I do 2 pi frequency, right, at 100 hertz would be 0.33 ohms. At 1,000 hertz would be 3.32 ohms, and would be 34 milliohms at 100 hertz, 330 milliohms at 1,000 hertz, and 3.32 ohms at 10,000 hertz. If you remember, before we were talking about milliohms, and was already pretty big. This is quite a big, quite a much larger than before. So what happens, right? What it means is that inductance opposes changing currents. Inductance opposes pulsing. And if you have a DC, inductance doesn't matter. If you have AC, as you increase the frequency, right, at 100 hertz is this 0.034. If we go higher, then we go to 0.33, 3.32, as we increase the frequency. What this means is that if we have high frequencies, we're going to have a very hard time passing them through our cables. And you'd say, okay, I don't have high frequency, but imagine you have a small pulse, a low frequency pulse, could be a 100 hertz square wave pulse. And the square pulse, or in the case of STT, if you remember, STT had these crazy jumps and down and up and down and very sharp turns. Those can be decomposed in doing your favorite Fourier series. You can decompose any pulse into a series of pulses that involve many frequencies. The sharp edges are associated with the high frequencies. What this means is that if I have long leads that have a high impedance, I'm going to be filtering the high frequencies that give us sharp edges in our pulses, and I'm going to have a dull pulse. So if you are paying big money for a machine that gives you fancy waveforms, we have a square wave, right? This is a square wave in blue. And what we have here in red is a sequence of the harmonics that would go, that would form this square wave. So you're gonna see that starts like with something like a sinusoidal, then a dented sinusoidal when it's double the frequency. You see it in action now. And as you have higher and higher frequencies, you start to get the sharp edges. If I have an impedance, these high harmonics, they die. Yeah, some of you, I know, play music. You have a good guitar, it's full of harmonics, sounds awesome. You're Joe Satriani. You buy a cheap guitar and you have no harmonics, right? It doesn't have this richness of sound. That is what the long cables do for you, right, in welding. So you're gonna see that when you have long cables, you tend to use DC. And when you want to use pulses, you have machines that have short cables. Quite interesting. So voltage loss at the contact tip. So we already discussed the resistance of the cables. We discussed the impedance of the cables, just to make sure we're on the same page. So if I'm welding in DC, what should I worry more about, the resistance or the impedance? Can somebody tell me? If I'm welding in DC, constant current, let's say, should I worry more about the impedance or worry more about the resistance of the cables? Resistance, of course, resistance. In DC, the impedance, we don't care. But if we have pulses, we have to worry about the length of the cable. So let's say we killed cables, we understand it. The other part we haven't discussed yet was at the contact tip, there is a sliding contact resistance. And this sliding contact resistance, of course, is not in any book. It is in a few papers. Companies measure it. They spend a lot of money and time measuring this. Of course, it's very proprietary. And it depends on things like how much pressure you put. If your contact tip wears out, this resistance changes, right? So you'd not believe like how important this is. When I was still in Colorado, we had a really cool project in which was all about measuring the wear of a contact tip and the consequences it would have. A contact tip costs about $1, but affects the performance of a $5,000 to $10,000 machine. And you know what? People don't want to pay more than $1 for a contact tip. And pretty much every time you have a problem, you can trace it back to a worn out contact tip. So in this class, we're gonna give it a value of resistance of more or less 2 milliohms to the contact resistance of the contact tip for all wire diameters. But things change. To give you an idea, if I put more pressure, I have less resistance. Same with the thermal contact resistance, right? More pressure, better conduction. That means that if I have a wire that has a tighter cast, it's going to be pressing harder into my contact tip if I don't do a good straightening, right? And I might have a different resistance of the contact tip. Now I have lower resistance, but I might be grinding my contact tip, right? That's something that's one of the problems with wires that have a tight cast, right? Look at this. What is the consequence of this voltage loss, this resistance at the contact tip? At 200 amps, we have about 0.4 volts. That is about 80 watts. 80 watts are generated right at the interface between the wire and the contact tip. If we are at 400 amps, it's more or less 0.8 volts, right? That's 320 watts, all there. Some of that energy goes into the wire. Some of that energy goes into heating your torch, right? That's why automated torches sometimes are water cooled if you're going to be using them for a long time. The contact tip can get real hot. Contact tip can be 50 degrees and actually can be more than that too, from this energy that is generated there. The frictional heating is close to zero, right? But this contact resistance matters a lot. All right, so I will stop here, but we're gonna have our seminar, and Alejandro prepared some calculations for you to calculate voltage in TIG and voltage in MIG on things I didn't get to discuss fully, but he will explain to you. And we'll wrap this up on Thursday. Let's stop here. I'll see you in 10 minutes.